Push down automata accept context-free language. In this particular lecture, we will describe how, or we will prove how push down automata, which basically a stack and the input stream and some sort of transition metrics or transition states will accept a free context-free language. This is a very important proof, and on its own time it was a key proof, because if I wanna find out how I can understand a context-free language, it will be established as this push down automata. So we will go through a few examples, and as I always say, this is also available on podcast. If you cannot follow the video because of bandwidth or because you are driving or so, you can basically stop the video, download the podcast. You have also access to the PowerPoint slides, so you can follow up, and I will keep repeating the PowerPoint slides so you can follow the flow of information. If you have any questions, just send them by email.
This video is subject to copyright owned by not. To maximize the use of this session, please connect a headphone and mic if you can. Stay in a quiet place. Adjust the sound of your computer. Close all other programs running on your computer. The instructor will direct you to open any other required program to use. Close chat programs in social media such as Facebook, Twitters, Messengers, WhatsApp, etc. Maximize your screen to see the four corners on this slide on your screen.
So if I go to slide number 4, the theory or the assumption here is I have a context-free language, and this will be equivalent to the language accepted by push-down automata. So if I want to have this proof, I will prove the first step. That's context-free language are subset or equal to the set of languages accepted by push-down automata. So if I want to convert any context-free grammar into a language, so the language of the grammar will be equivalent to the language of the machine accepted by the push-down automata. Step number 2 is I will say that the context-free grammar or context-free language of grammars is actually, it belongs to the language accepted by automata. So I will convert any push-down automata language to a context-free grammar with language of the grammar will be equal to the language of the machine. To be able to do the proof, I will convert the context-free grammar to a push-down automata. So I will take any arbitrary context-free grammar, G, and the context-free grammar, we will convert G to a PDA, a machine, such that the language of the grammar will be equal to the language of understood by the machine. So for each production in G, A to W, where I have, I can add the transitions, and for each terminal A, I can add these transitions. So in this case, I will build this machine where I will have from the initial state to the accepting state, the transitions, which is empty, where empty leading to the starting, and empty where S or the end of the stack leading to the end of the stack. So that's why I will have the accepting. So here's an example. If I have this particular grammar where I have the production S starting symbol, A starting T, capital T and B, and S can be production of B, T can be TA or transition TA, and T can be also the empty. The push-down automata will be described in this way, and this will be the transitions between Q1 as long as I have Q1. So the PDA or the push-down automata simulates the left derivation. The grammar on the leftmost derivation will look like this grammar, where I will keep adding sub-expressions. The PDA computation, if you remember in the last section, we talked about how to represent using the initial symbol, the input stream, and the stack content. and I will start from the initial state to the next state. So if I do the leftmost derivative, I will have the terminal, the leftmost variables, and I have the variable of the terminal, and the production will apply where I will have terminals, variables, and variables as applied. So the grammar in the left most derivative, the production applied will be a function of production between I to j, and it end up to be capital BZ. The computation will look at these transitions applied. So if I have an input sigma I I will read the input and then I will remove from the stack, and this will be the transition applied. Once all the symbols sigma I, sigma j have been removed from the stack, the last transitions applied, which basically sigma equal to empty, and this will lead to the variables and so on. So if I want to get an example, I have here the input AB, AB, and at time 0, this is the automata. Here's the finite, the push down automata, or the transition. So I will go with B. I will start with the start symbol, and then I will add the symbols A, S, T, B, and then I will remove the symbols, and I will go to time 4, time 5, time 6, times 8, times 9, and then it will accept it. So in this way, this is the grammar to the leftmost, and this is the equivalent computation or the equivalent translation of the computation. So in general, we can show that the grammar generated by the string WG, if and only if the PDA accepted, therefore the language of the grammar will be equivalent to or equal to the language of the machine. To prove step number 2, we convert the PDA into a context-free grammar. So we will convert the machine M into a context-free grammar G. So we will look at L language of M will be equivalent to the language of G. So to modify the push down automata M so that the PDA has a single accept state, use 2 initial stack symbol. Once acceptance the stack contains the stack symbol, the symbol not used in any transitions. Each transition is either push a symbol or pop a symbol that are not doing both. So I will have here the single state. I will use the initial stack, which will be the hyphen. At is an auxiliary stack symbol, and Z is the initial symbol in the stack. And this will give me the PDA, or the machine that will produce or generate the sequence of the stack. Once accepting the stack, it contains only the symbol hash. It means that this symbol is not used in any transition, which means that this is the acceptance symbol. So each transition either push a symbol or pop a symbol, but not both. Remember, in the previous examples, we always say it's a push, or you can pop one symbol and push 2. Here we only do one symbol at a time. And here is the push and pop. So this is assumption. Now the M4 is a final modified PDA. Note that all the initial symbol stack is hyphen. It never been used in any transition. So we'll have here an example. So I have this M, and I will take this M and I will reduce it to the machine 4, where I will take the initial to be Q node, and then I will take it to Q1, then Q1, and I keep actually splitting this this machine to produce this version. And the grammar constructions here is I will have the states of the PDA, which is Qi, Qj. Kind 1, for each state, the grammar, like if I'm standing in a state Q node, the grammar will be AQQ lead to empty. And if every 3 states QBR, so ABQ will lead to APR, ARQ, sorry. And for every pair of transitions, A empty to T R, so ABQ will lead to ARS, B. Initial state and accepting states, this is the starting variables for the grammar. Here is an example of the PDA. Here is an example of the grammar. And here is the example of the triplet states, and here is the pair of the transitions. So in this case, I suppose that the PDM converted to grammar G, so I can prove that the language of G will lead to the language of M, or equivalently, LG will be subset of LM, and LG is belong to LM. So in this case, we need to show if G has a derivative, the string of the derivative will be also accepted by the machine M, and if G has a derivative, then there is a computation in M where it will lead to conclusion or to accepting states. Therefore, we have these transitions, which basically from the initial state to the final states, and if we have the symbol star or hash, the symbol hash will appear at the stack. So what we demonstrate right now is the original proof that any context-free language will be by push-down automata. You need to read the proof and understand it. However, you may not be required to be writing the proof. So it's just one of the point of completion for this material, that there are some topics which you have to be aware of, not really studying. Lemma 1, if ABQ producing star W, which is a string of terminal, then there is a computation from state P to Q on a string W, which leaves the stack empty, which means that symbol BQ will be accepted, or the string BQ will be accepted. So, and here shows how we do the proof intuition, that ABQ will lead to the sequence W. So ABQ will be ARQ, which is splitting, which will lead to W, or it will be type 3, which basically ABQ lead to ARSP, which will be to W, and then I will be able to do type 1 with the stack height. I will be able to do type 3, and the formal proof, we formally prove this claim by induction on number of steps of derivative, which basically is the number of steps. Induction basis, kind 1 is a production which get APP into empty, and therefore B equal to Q and W equal to empty, and the computation will lead from which will be a star production of B empty empty equal to P empty empty. The induction hypothesis is there is a k derivative steps to lead from ABQ to understand W, where suppose that BW empty will lead to B empty Q or empty stack. The induction will be, you will prove it at the k plus 1, and at k plus 1 we can do the derivation as well, and from this we will be able to prove it at step k and step k plus 1 for both cases. So this is a kind of proofs were required early on, that because we want to prove that any context-free language can be done by push automata. So far what we have is language of context-free grammar is a subset of language of machine by a push-down automata. Language of grammar belongs to language of machine, and therefore LG equal LM, or LM will be able to understand LG. As I said, this is a historical proof. It's one of the basic series which proves that we can use context-free grammars and context-free language, and we use a stack to be able to understand this language. As I said, that's just for completion and illustration. You may want to review it before an interview. However, for an exam, I wouldn't consider it. If you have any questions, as usual, we always say send me an email or write it in the comment below, and looking forward to meet you again in the next